Now here is the circuit that we're going to experiment with, testing this latching Hall effect, part number U18, manufactured by UTC. Now 6 months ago, has it been 6 months? Yes, it has. Where'd the time go? Ah well, 6 months ago I experimented and put up a video with this circuit right here. We made changes. We modified that circuit. Let me show you that circuit real quick. We'll refresh our memories. Move this out of the way here. There we go. Let me move this over just a skoshie bit so we can see it. Here is the circuit, and this portion over here is identical. The differences between our modified circuit with the latching Hall effect is that the 16 kilo ohm resistor in the base circuit here was tied to a switch, and on the other side of the switch we had 5 volts. And we had this 100 kilo ohm resistor down here. The purpose of the 100 kilo ohm resistor is that when the switch is open, we don't want the base to float, so we connect the base to ground through the 100 kilo ohm resistor, ensuring that that NPN transistor is turned off. So there, I'll put the video up. I'll put a link to this video of this circuit right here, and you can go back and watch that. That was a lot of fun. I did a lot of calculating in that video so that you'll be able to determine through calculations how to select the base resistor and also how to select this current limiting resistor up here in the LED circuit. So here is our modified circuit. I removed the switch and tied the 16 kilo ohm resistor directly up to 5 volts. I removed the 100 kilo ohm resistor that was in the base circuit going to ground. I removed that and replaced it with the Hall effect. The way this works, this is a latching Hall effect. It has open collector output, so that when I apply a south pole to the face of that Hall effect, the output through the open collector NPN transistor is connected to ground. You have collector emitter. And so that in effect, you have 0 volts on the output because it's connected to ground. When I apply a north pole, that unlatches that latching Hall effect, turns it off. And so that now the open collector NPN transistor is not conducting to ground. And we have this 5 volts up here places a high through this 16 kilo ohm resistor at the base emitter junction right there. So that when that Hall effect's off, we would in effect have around 0.7 about from base to emitter. We have 5 volts up here, and we have about 0.75, maybe higher volts right here. That drives this transistor into saturation, and we have full conduction from collector to emitter, and current flows from the plus 24 volt DC power supply through the relay coil, through collector emitter to ground. And when current flows through that coil, we have a magnetic field built up in that relay coil, and that pulls this contact closed. And now we have current flows from the plus 24 volt DC power supply. That's the same power supply that's turning on the relay. Current flows from that power supply through the 1.2 kilo ohm current limiting resistor, through the anode cathode junction of that green LED, through the closed switch to ground, turning on that green LED. Now I used two supplies, the 24 volts for the relay coil and the LED circuit, and I used 5 volts for the Hall effect and the base emitter bias of this resistor right here. Isn't that neat? Let me show you a block diagram, if I can put that up there, of this Hall effect device right here, the latching Hall effect. From the block diagram of U18 latching Hall effect, we can see that the output is open collector. And that's why we have to have that 16 kilo ohm resistor pulling this collector up to 5 volts. That resistor is the collector resistor. Here's the breadboarded circuit. Here's the Hall effect, the NPN transistor, the base resistor pulled up to 5 volts. Here's the relay, the 24 volt DC coil relay, spike suppression diode, LED, and its current limiting resistor. Now right now, the Hall effect is turned on, pulling the base voltage away and to ground through the open collector output of the Hall effect. When I apply a north pole, the Hall effect is turned off, and it latches. It latches in the off state and the on state. And so now 5 volts through this 16 kilo ohm resistor is applied to the base of the NPN transistor, causing it to go into saturation and turning on this relay right here. And when the contacts close, the LED circuit is connected from 24 volts through the contacts to ground. The Hall effect is on, and now we have 0 volts applied to the base, turning the NPN transistor off. Hall effect is off. Hall effect is on. Hall effect is off. Hall effect is on. So if this horseshoe magnet is marked correctly, to turn the Hall effect on, to latch it on, we have a south pole applied to the face of that Hall effect. And to unlatch it, to turn it off, we have the north pole. Here we have the fluke voltmeter connected to the base of that NPN transistor. The base of the NPN transistor is connected to this 16 kilo ohm resistor that's tied to 5 volts, and the base is also connected to the output of the Hall effect. Now you can see the base voltage is 3 millivolts DC. That indicates to us that that Hall effect is turned on, pulling the base to ground through the Hall effect. This is our base emitter voltage, 779 millivolts DC. That is the base voltage, base emitter voltage. Hall effects turned on, 3 millivolts DC on the base. And that transistor is turned off. Hall effect is turned off, and we have a base emitter voltage of 778 millivolts DC, 0.778. 3 millivolts DC, 0.778 volts DC. Switch is pretty fast, doesn't it? Well, I hope you enjoyed that video. That was a lot of fun. That was a lot of fun. I'll put these drawings up at the end of the video. And again, I'll provide a link to this other circuit right here so you can see how to analyze this circuit and how to perform these calculations based upon that 2N3904 transistor and the resistance of the coil here. Two fascinating videos of very simple circuits to breadboard. Not too awfully hard. Looks complicated, but once you know how it works, it's fairly simple. Have a good day, all, and we'll see you next time.